momentum. We're going to mostly be talking about linear momentum today. So hopefully you already know it's the property or tendency of a moving object to keep moving. Momentum is a vector quantity. That's the symbol we usually use for momentum. And it's equal to an object's mass times its velocity. Once again, I've got somebody trying to get in, so give me a second to let them in. All right, let's try again. So as I was saying, momentum is a vector quantity. It's mass times velocity. The direction of the momentum is the direction of the velocity. The units we're going to get are either kilograms times meters per second, mass times velocity units, or we can also write that in terms of Newton seconds. We'll talk more about that here in just a minute. These are the equations you're going to see on the AP Physics sheet, the formula sheet for momentum. We'll talk about both of those equations here momentarily. All right, let's see. We got people trying to pop in. Let's see if we can't let them in real quick. All right, so this one is just a basic momentum equation. Mass times velocity. This one is change in momentum equals F delta T. We're going to talk a lot in a minute about change in momentum and impulse, or what we call the impulse equals change in momentum. F delta T is sometimes called impulse. It's a force applied over time, and that can cause a change in momentum. I often like to write this equation, though, as F delta T equals M delta V, where this is the change in momentum, and this is the impulse, which we usually abbreviate as J. Why J? I don't know. All right, so trying again here. So the rate of change of momentum is equal to the net force applied to the object. This is essentially another way of writing Newton's second law. It's actually how Newton first wrote it. So remember, we had just a second ago that F delta T equals change in momentum, or F delta T equals M delta V. Well, if we do a little bit of rearranging of that equation, and we move this delta T over to this side, essentially we end up with F equals M times delta V. So this is another way of writing Newton's second law. F delta T equals M delta V is just another way of saying net force equals mass times acceleration. Another way of writing it. Here I think we see all that again. Impulses, which again is the F delta T part of that equation, which we symbolize with the letter J for some reason. Impulses cause changes in momentum. They're forces applied over time. This is why I mentioned a minute ago that sometimes for changes in momentum, we'll see NS as the units. And a Newton times a second is the same as a kilogram times a meter per second. Same unit, different way of writing it. Maybe we'll get everyone in here in a second. All right, so just a little bit more about impulse and momentum. Let's think about a golf ball situation. When you swing a golf club, you swing it hard. So there's a large force, and that's applied over a pretty short time. That can cause a pretty big change in momentum. remember, this is our equation. You're not changing the mass of that golf ball. So what you're changing is the velocity of that golf ball. And you can cause a big change in velocity either by applying a really big force or by applying that force over a long time. And that's one of the reasons when you swing a bat or you swing a golf club, you follow through. And that follow through increases the amount of time that the club or the bat is in contact with the ball. And therefore, it gives it more impulse and therefore a bigger change in momentum. Sorry for flipping back and forth here. All right, another way to think about this is with an airbag. So when a car hits something, if the car stops instantaneously, let's say old cars are pretty much solid still. If they hit something that was solid, that car stopped instantaneously, which meant the time over which the force was applied was really small, which meant the force had to be huge. And that force was essentially eventually passed on to the driver in the car, the passengers, and that caused damage. What an airbag does is it increases the stopping time for the person if this time goes up, the person's change in momentum has got to be the same. They were going a certain speed, they're going to stop. Part doesn't change. But if you increase the stopping time, that means you decrease the force acting on the person. And that's important. That's also why a lot of cars are designed now with crumple zones. They're made to brake, but brake in sections so that the time for stopping goes up and therefore the force required to change the momentum goes down. Makes for safety. So a breakable car is actually maybe more safe than a big solid hunk of steel. All right, let's continue on. So another thing you're going to see when you're talking about momentum are force versus time graphs. You guys know that when you find the area under the curve, regardless of what you're finding the area under the curve of, when you find this area under the curve, all this blue area, essentially what you're doing is you're multiplying the y quantity times the x quantity. And remember that force times time, or force times change in time, is impulse. So when you have a force time graph and you find the area under the curve, you're finding the impulse. Or remember that the impulse is also equal to the change in momentum. So by finding the area under the curve, you're finding both. You're finding the impulse and you're finding the change in momentum. Those are historically kinds of graphs that show up on the AP exam. Since they're changing this to an all FRQ test, I don't really know yet. Hopefully we'll know more after tonight. But I would know that a force time graph, if you find the area under the curve, you can get the impulse, which is also equal to the change in momentum. Let me let these last couple folks in here. Oh, maybe not. Try it again. So two big ideas when we're talking about momentum. F delta T equals M delta V. Impulse equals change in momentum. The other one is the idea of conservation of momentum. The idea that the total momentum of a system, and this is an oscillated system, where there are no outside forces acting, it's conserved. So let's say we have two objects, object A and object B. That's the momentum of object A before the collision, before the explosion. This is the momentum of object B before. This is the momentum after for A, and this is the momentum after for B. An oscillated system, as I said a second ago, is one in which the only significant forces are those that act between the objects. There's nothing outside. The sum of the internal forces, therefore, acting on the system is 0. There's no external forces acting on this system. That's the only time this is going to work, when it's a closed system. We're going to talk about a couple of types of collisions. And the two main types that we'll mention in this class are elastic and inelastic. During elastic collisions, the objects collide and they essentially bounce off of each other. During these collisions, both the momentum and the total amount of kinetic energy in the system are conserved. So both those are conserved, momentum and the total kinetic energy of the system. That happens during elastic collisions. The other type of collision is called an inelastic collision. And in these collisions, usually what happens is that the objects collide, and lots of times they stick together, or something happens where they convert kinetic energy to heat, typically. Typically, the problems we're going to see, they stick together. The objects move together as one object with the same velocity. During that collision and that deformation that happens, some of the kinetic energy is converted to other forms of energy, as I said before, like thermal energy, like sound. In these kinds of collisions, momentum is conserved, but kinetic energy is not. The kinetic energy after the collision is going to be less than it was before the collision. That's the system kinetic energy. All right, another thing that we need to think about when we're talking about momentum is the center of mass. You're never going to have to calculate the center of mass in AP Physics 1, but just know that the center of mass is the point in a system of objects or particles that moves in the same path that a single particle would move if subjected to the same net force. What I need you to realize here is that the velocity, the momentum of the center of mass is not it's not going to change during a collision. We're going to see several problems where that's the case. So when you're thinking about a system, think about the center of the mass of the whole system and how that velocity is going to be conserved for that center of mass. That's sort of what I'm saying here. The linear momentum of an extended object or a system of objects is equal to the product of the total mass of that system and the velocity of the center of mass of the system. Because we're dealing with closed systems, it's conserved. The velocity of the center of mass does not change during collision or explosions. Every AP exam lately, they've asked questions about this. We're going to see some multiple choice questions later today. We may even get to an FRQ where they ask about this. So during a collision or explosion, the velocity of the center of mass of the system doesn't change. All right, so let's look at some problems. We're going to start off by looking at some short kinds of problems, mostly multiple choice kinds of things. I realize these aren't going to be on the exam, but they may be just in an FRQ format. And then either toward the end of today or for next session, we'll start looking at actual FRQs. So here we go. A box slides across a horizontal frictional surface. I'll tell you what, I want you guys to take about 30 seconds and try this question on your own, and then I'll actually go through and work it for you. So see what you can do with this question on your own. All right, what I'm hoping you remember here is that for a force time graph, if you find the area under the curve, you're finding the impulse, which is also equal to the change in momentum. So in this case, to find that change in momentum, we need to find the area under the curve. There's a couple of ways we could do this. First of all, you might realize this is a trapezoid. And you might realize that the area under the curve of a trapezoid is 1/2 base 1 plus base 2 times height. This is going to be the easiest way to work the problem. The other way you could do it would be to divide this into a triangle, and a rectangle, and calculate the areas of each one of those. That's going to make it a little more tricky to work this out. I'm going to do it with a trapezoid. So my area is going to be equal to 1/2 base 1, which I'll call the top, and that top runs from 2 to 4. So that top is length 2. The bottom is from 0 to 6, so length 6, times the height. And the height we have is just F max. We don't have any units, so we're just going to write F max for the height. So my area is 1/2, 2 times 6, or 2 plus 6, which is 8. So that's 4. 4 times F max. So since we're applying the force, the momentum of this box is going to increase. It's going to increase by 4 times F max. And we know it's increasing because the box is moving to the right and the force is applied to the right. It's a positive force. All right, here's question 2. Take just a minute and try this one out on your own as well. All right, so here's question 2, or the answer to question 2. So we've got this box sliding across a frictionless horizontal surface. It has a velocity of 5 meters per second. It collides with and sticks to a 6 kilogram object that was initially at rest. We're looking for the speed of the objects after the collision. Well, because these collide and stick together, this is an inelastic collision. So to work this problem, we're going to use the law of conservation of momentum. Momentum before equals momentum after. So here we calculated the momentum of the moving object before the collision. Its mass times its velocity. The momentum of the second object was just 0 because it wasn't moving. Afterwards, we've set that equal to the sum of the two masses because they stick together. So that's going to be the 4 kilograms plus the 6 times their velocity after the collision. That's what we're looking for. So if we solve that out, over here we're going to have, on the left, we're going to have 4 times 5. So that's going to be 20 kilogram meters per second over on the left. And that's going to be equal to 10 kilograms times V1 prime. So we divide by both sides by 10 kilograms, and we end up with 2 meters per second. That's our answer on that one. All right, moving on to question 3. This one, same problem essentially, but this time we're looking for the total, for the change in total kinetic energy. Remember that in inelastic collisions, kinetic energy is not conserved. So let's calculate the kinetic energy before and the kinetic energy after the collision. All right, so let's move this up here out of the way. Somewhere out of the way. Let's just delete it. How about that? So in the previous problem, we found the final velocity of the two objects when they were connected was 2 meters per second. We need to calculate the kinetic energy before and after the collision. So before the collision, the only thing that had any kinetic energy was the 4 kilogram box. So we're going to use kinetic energy equals 1/2 mv squared to calculate that. And you can see me doing that right here. 1/2 mass of the first box times velocity of that box squared. We end up with 50 joules of kinetic energy before the collision. Remember, the 6 kilogram box didn't have any kinetic energy because it wasn't moving. After the collision, again, using the same equation, we're going to take 1/2 times the combined mass, because now they're stuck together. So that's 10 kilograms, times the velocity that they're moving off together, which is 2 meters per second. Don't forget to square that. So work that out. We end up with 20 joules. So this is the kinetic energy after. We're looking for the change in kinetic energy. Change in anything is going to be final minus initial. So our final kinetic energy was 20. Our initial kinetic energy was 50. So 20 minus 50, we get a change of kinetic energy of negative 30 joules. So answer C was correct here. And remember that negative 30 joules, it can't just go away. It's not used up. It's converted into another form of energy. In this case, probably some of it's sound, probably some of it is heat or thermal energy. All right, here's question 4. And this one's tricky. My students over the years have always missed this question. A 0.1 kilogram tennis ball moving to the right at 42 meters per second collides with a wall and bounces off to the left at 38 meters per second. What is the ball's change in velocity? Remember, change in anything is its final minus its initial. What you've got to realize here is that the final velocity is moving to the left. So that means that final velocity is negative 38 because it's going to the left, negative 38. The initial velocity was positive 42. It's moving to the right. So final velocity, negative 38, minus initial velocity, positive 42. So when we subtract those, negative 38 minus 42, we end up with negative 80 meters per second for the change in velocity. That kind of thing, people always forget that part right there and how that the negative 38 needs to come into play. That's critical. All right, question 5 is a continuation of that last one. Here we want to know what's the impulse that acts on the wall. Again, we need to remember that F delta T equals M delta V, where this F delta T is the impulse and the M delta V is the change in momentum. We don't know the force. We don't know the time. But what we do know is the mass and the change in velocity. So we can calculate the change in momentum, which is equal to the impulse. So our change in momentum is equal to M delta V. Our mass here is 0.1. And remember, we just calculated our change in velocity was negative 80. So when we multiply that out, we're going to end up with negative 8 kilogram meters per second, which is equivalent to a Newton times a second. So we're looking at D there as our answer. All right, here's a continuation of that same problem. Notice all the numbers are the same, but this part of the question has been added. So if the ball was in contact with the wall for 0.05 seconds, what average force was applied to the wall to the ball by the wall. So remember that impulse, J, equals F delta T. We calculated in the previous problem that the impulse, my computer's going crazy here, that the impulse was equal to -8. That's the impulse. We're looking for the force, and we know here that the time is 0.05 seconds. We'll worry about significant digits in a minute. So if we solve this out, we're going to divide both sides by 0.05. We're going to end up with a force acting on this of -160 newtons. All right, so here's another one. We got about 3 or 4 more of these multiple choice, and then we'll look at some FRQs. So we've got a 0.0750 kilogram ball moving to the left at 8 meters per second when it's hit by a racket moving to the right. The graph displays the force applied to the ball by the racket as a function of time. What's the ball's change in momentum? So this is another force time graph. And this is another one of those situations where we need to find that the area, we need to know rather that the area under a force time graph is impulse, which is also equal to change in momentum. So we just need to find the area under the curve. Here we have a triangle, and we know that the area of that triangle is 1/2 base height. So 1/2, the length of our base is 0.5 seconds. And our height here is 150 newtons. So we multiply that out. Half of 150 is 75, and then another half of that is 37.5. This is all positive. It's to the right. So we're looking at positive 37.5 kilogram meters per second. All right, so here it wants to know, what is the ball's change in velocity? Same situation. Everything's the same. We're looking for one additional piece of information, the change in velocity. And what we've got to remember is that impulse that we just calculated, 37.5 kilogram meters per second, is equal to the change in momentum, which is m delta v. Well, we know m. M is 0.075. And what we're looking for is the change in velocity. So simply solve that out. And when we do, we come up with this. So it looks like our change in velocity is about 500 meters per second. And that sounds crazy, but remember that's changing not only the actual magnitude of the speed, but it's also changing the direction of the speed. All right, so next question. And this is one of those center of mass questions that we talked about a minute ago. A boy holding a medicine ball slides across an icy parking lot on a sled. The boy throws the medicine ball forward as the sled slides across the parking lot. Which of the following correctly describes the velocity of the center of mass of the sled boy medicine ball system just after the ball was thrown? Assume no friction or air resistance acts on any part of the system. All right, so this boy and sled and ball are all sliding. They're a closed system. The boy pushes the ball pushes back on the boy, so there's no net force acting on the system. This is another one of those situations where the center of mass, the velocity of the center of mass in a closed system does not change. The momentum of the center of mass in a closed system does not change. So that being said, the answer is D. The final velocity is equal to the initial velocity. Those are the final and initial velocities of the center of mass of the system. Those do not change. All right, so now let's look at a ballistic pendulum problem. I'd like for you guys to take just a minute and read this problem, just so you know what's going on. So let's take about a minute and let you guys read it, and then we'll go from there. All right, so here this ballistic pendulum, we're shooting a bullet into essentially a box, a bob. That bullet has a mass of 0.120 kilograms, and it's moving with a velocity of 300 meters per second. The bob isn't moving. So this bob has zero velocity, zero kinetic energy, zero momentum before the collision. All the momentum, all the velocity, all the kinetic energy initially is coming from the bullet. We want to know what is the velocity of the bullet bob system just after impact. We're assuming that the bullet gets embedded in the box as it goes here. So this is going to be a conservation of momentum problem. Going to look something like this. It's an inelastic collision. These objects stick together. So again, we're using the idea of conservation of momentum. Momentum before equals momentum after. So we're going to put in the mass of the bullet and its initial velocity. The momentum of the bob before is zero. After the collision, the two objects are combined. So we combine their masses, mass of bullet plus mass of bob, and we're trying to find their combined velocity after the collision. Solve that out for V1, and we end up with a final velocity of 4.18 meters per second. So we're looking at answer A. All right, so question 11 is a continuation of that. We want to know to what maximum height will the bullet bob system rise after the impact. So after this bullet hits this box, the bob is going to be pushed up. And we want to know how high does it get pushed. What we've got to think about is just immediately after this, this bullet gets embedded in that box, all of the energy is kinetic energy. We just calculated the velocity of that combined system to be 4.18 meters per second. So just after the collision, just after the impact, the kinetic energy of the system we can calculate using 1/2 mv squared. And you can see that calculation being done right here. We took the mass of the bullet and the bob combined together times their velocity squared times 1/2 mv squared. And we ended up with 75.3 joules of kinetic energy. If we assume there's no friction or drag or anything like that, all of that kinetic energy as this bob pushes up is getting converted into gravitational potential energy. So essentially, we're going to set the kinetic energy initially equal to the gravitational potential energy up at its maximum height. So we're going to set 75.3 joules equal to, if you remember, gravitational potential energy is mgh or mg delta y. So our 75.3 is going to be equal to the mass, which is, what is our combined mass? 8.62 kilograms times g. Here you see I use 9.8, but remember on the AP exam, they always want you to use 10 meters per second squared. So if we calculate that out, it's looking like when I use 9.8, it came out to be 0.891. When we use 10, it's not going to come out to be exactly that, but very close. Let's go ahead and calculate out that what that would be using 10 meters per second squared. Let me get a calculator real quick. So it's going to be 75.3 divided by 86.2. So we're talking about 0.874 if we use 10 meters per second square, 0.874. And it's going to be 0.874 meters. All right, I'm going to deal with question 12 on the next webinar because it deals with elastic collisions. And that's a little more tricky to calculate. So I'm going to save that one for the next webinar. We're going to go ahead and talk about one of these free response questions today. Next time, we'll talk about question 12, elastic collisions, and we've got two other momentum FRQs we'll deal with in the next webinar. But we'll end today by talking about free response question 1. So if you guys would take just a minute and read part A, look at the data table, and we'll go from there. All right, so as you see here, we have a cart. It's rolling with no friction along a horizontal table until it collides with another cart. We get the position time graph, or position time data rather, for the 0.6 kilogram cart down here. So at time 2 seconds, right here, is when the collision happens. And it's an inelastic collision. And we want to know what's the velocity of the two carts immediately after the collision. Well, this is another one of those conservation of momentum setups where we've got to know the momentum before and that's equal to the momentum after the collision. But the first thing we need to do is to use this table to determine what the velocity of the 0.6 kilogram cart is. So this is position time data. Remember that you can find the slope of a position time graph to get your velocity. So what we can see is that every time interval, we're increasing with every time interval of 1 second, we're increasing a distance of 20 meters. So I'm hoping you see that the velocity is 20 meters per second and that it's constant because the amount of distance for each time between each time interval is going up. If not, you could just find the slope of this data. If we were graphing this, we would graph it as position versus time. So we could take any 2 points and go from there. So we could have, let's just take the last point, which would be 240. And let's take 0, 0 as our first point. And we could calculate the slope between those points. So we could go 40 minus 0 over 2 minus 0 and end up with 20. The speed is 20 meters per second. That's what we need to get from this data, and it's constant to begin with. That's for the 0.6 kilogram cart. So you probably would have got a point if this was an FRQ for finding that speed, 20 meters per second. Remember, this is an inelastic collision, so we're going to use the law of conservation of momentum. I would go ahead and, first of all, write out that equation, just so they know you know what you're doing. Then plug in numbers. So this was the mass of the original cart, 0.6. That cart was going 20 meters per second. The second cart had 0 momentum to begin with because it wasn't moving. And that's equal to the combined masses, 0.6, 0.85, times the new velocity after the collision. Solve that out for V1, and we end up with a final velocity of 8.28 meters per second. All right, so part B is maybe the most tricky part of this whole question. Take a minute and read part B for me. All right, so here's what our graph ought to look like. So the solid line is the 0.6 kilogram cart. At time 0, that cart was moving at positive 20 meters per second. And it did that all the way up until the time of the collision, right here, which happened at t equals 2 seconds. Once that collision happened, its velocity dropped because it was losing some momentum. Some of its energy was converted to heat. And that collision happened over 0.5 seconds. So we can see that velocity drop, 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 drop. That continued to happen until we got to t equals 2.5 seconds, where now both carts are combined and they're moving off at the same velocity. And that velocity we calculated earlier to be 8.28 meters per second. So that's what we're seeing there. Now for the other cart wasn't moving at all. So its velocity is 0 all the way up until 2 seconds. Right there, the collision happened. During that 0.5 second collision time, we see its velocity starting to go up, starting to increase. It's accelerating. It accelerates up to the 8.28 meters per second, and then it continues at that speed. All right, some important things to think about when you're doing graphs like this. Make sure you label everything, include units. Make sure that if you have more than one line on your graph, that you use a key and that you make sure that people can tell which line is which. You may have to do solid and dashed. You may have, if you have different color pens, whatever you have, make sure that you make a key and that people know which line is which. And be neat. Let's go ahead and look at part C. What impulse acted on the 0.85 kilogram cart? Justify your reasoning. All right, so what you got to think about is that the cart initially had 0 momentum. After the collision, the cart's momentum was 0.85, its mass, times its new velocity, which was 8.28 meters per second. So if we multiply that out, let me go ahead and go to the answer key here. So its change in velocity was 8.28 minus 0. That means its change in momentum, and therefore also its impulse, because those two things are equal, was 0.85 times 8.28, which ended up with an impulse of 7.04 Newton seconds. Alternatively, we could write that as kilogram meters per second. All right, let's end this thing up for today by talking about parts D and E. Part D wants to know how much mechanical energy was converted to heat or sound during the collision, and justify your reasoning. Remember, mechanical energy is the sum of the kinetic and potential energies of a system. Here we're not really dealing with potential energy. So really we're talking about kinetic energy in this problem. So what we need to think about, first of all, was how much kinetic energy was there before the collision? Remember, K equals 1/2 mv squared is our equation. So here I calculate the kinetic energy of the original cart, the one that was moving. It's 120 joules. After the problem, the two combined carts have kinetic energy. So we're going to take their combined masses. We're going to multiply that by their velocity, 8.28 squared. We end up with this much kinetic energy after. Well, we're looking for the change in kinetic energy. Remember that change in anything is really final minus initial. So we really ought to take 49.7 minus 120. And we should really end up with negative 70.3 joules. Negative 70.3 joules. Remember, when you're calculating a change in anything, final minus initial. So we're losing, the negative means we're losing 70.3 joules of energy as heat and probably some sound. All right, so part E, calculate the velocity of the center of mass of the two-cart system before the collision occurred. Describe the process or logic that you used to reach this conclusion. Here's what I told you we would come back to. Remember that the velocity of the center of mass does not change during a collision. It's conserved. We don't have enough information at the beginning of the problem. Let me go back to the beginning for you. To really calculate where the center of mass is even. We probably could with a lot of work, but it would be tricky. But what we can do at the end very easily is we can calculate the velocity of the center of mass at the end of the problem. That's what we know at the end of the problem is that everything is moving at this speed. That's the velocity of the whole system. So that's also the velocity of the center of mass. If that's the velocity of the center of mass at the end of the problem, it was also the velocity of the center of mass at the beginning of the problem. Because during collisions in a closed system, the velocity of the center of mass does not change. So that's what they're looking for you to talk about on part E. Give them the number and tell them that momentum is conserved. The velocity of the center of mass before the collision is always the same as the velocity of the center of mass of the system after the collision. All right, that's where we're going to stop today. Let's take a minute and take any questions you might have. And remember, next time we're going to talk about elastic collisions, and we have two more FRQ questions that we're going to work through. One of those is a bit tricky. Do you have questions from anyone?
Yes, sir. So quick question for impulse. Should we use NS or kgm over S?
Either one is correct. They usually for impulse use Newton seconds, but both are the same unit. So it doesn't really matter.
Okay, thank you.